Hi, welcome back to another video. My name is Dan, and today I will teach you how to derive the famous Minkowski-Einstein energy-momentum relationship. And in this video, we also prove that light has no mass. So this equation we see here is pretty fundamental because it has energy, mass, and momentum separate completely. It means for a photon, which is the mass is zero, we have the equation E equal bc. But we see that there's also two equations that we can work simply using Lorentz transformation. But the problem that is include the gamma here, which is must be infinite for photon if you think about this. So for a photon which is traveled at the speed of light, we have that 1 over minus v squared over c squared, which is v here is actually the speed of light. So we end up with 1 minus c squared over c squared. This term is actually 0. So we have an undefined problem. So we have either this thing is roll up to positive infinity. We know that infinity doesn't make sense here. So this equation, both of these equations do not work for light. So before we prove it, we have to have a concept of the forward velocity vector. So the forward velocity vector, what can we make about them? Remember, in special relativity, we treat that proper time as invariant. So we can write something like this: dt over d tau, dx over d tau, dy over d tau, and dz over d tau. We can also show the another convention where we write t at x0, x at x1, and x2, x3, but I think it's more confusion than necessary. So the first is we treat proper time as invariant, and we can make the expression as derivative with respect to proper time. But we immediately see a problem. For a vector, this term is actually velocity, but this term is actually less unit because this time measured in second and this also measured in second. So I have to add speed of light here to balance the units out. And we have to know the second concept is that in relativity we have the four momentum equation, which is this look exactly like the classical version of the free momentum. But this u is actually a 4 vector, which is this one. So we can see clearly that B, so we have to use the dot product in order to find this term square. Let's go to the mass square because it's a scalar, and then we simply say that u dot u. So we have to know how to u dot u. The first proof that u dot u must equal to something that we have to use the Minkowski metric, which is ds square equal to c square. Let me make this table more empty now. It's so full now. We remember the geometry relationship, which is tiny distance square equal to c square dt square minus dx square. Then that we can derivative this. We can derive for dt square as well. So we can make this term a derivative square. And we have here is just sorry, I forget that this term is actually proper time. We can then make this proper time relation. Sorry. So this is equal to proper time square. So we have this over proper time. We have to write this. so we can work out here. So first of all, we can improve the momentum, as we know that ds equal to cd tau by the logic of Minkowski geometry. We can pretty sure that this is the speed of light square. But how do we prove this? Well, technically there are two approaches. So let me show you an equation in general relativity, which is ds square equal to the metric tensor component multiplied by the position u and v. So this metric tensor is a matrix that looks like this when space-time is Minkowski flat. But if we move to general relativity, we know that space-time can curve and the expression can look very different. So this is where the Pythagorean theorem doesn't work, because for the Pythagorean theorem we have this is 1 0 0 and 1. So we know that Minkowski geometry doesn't work like the Pythagorean theorem. So it means that we have to write this as ds square equal to c square dt square minus dx square. This minus sign here is where it comes from. So this minus sign here is where we have this c square in this. So this metric tensor is actually a dot product. So we can expand the sum, but I think do it will make the time will be, we have not enough time, right? So we come back to the original problem of velocity vector. We know that for one thing that dt divided by d tau is actually gamma, because we can use in the Lorentz transformation v equal to gamma divided by t prime plus v over c square times for s prime. So we know that we can make these things delta, and we know that at delta x prime approach to 0, we have that delta t prime equal to delta tau, because an object event happen at a position of an object which is fixed. Then we know that the time between two events is actually due to time dilation. So we also have that delta t equal to gamma delta tau. So we know that this thing is equal to gamma. Okay, so we can make an adjust. We can move the speed of light into the time component first, because why? dt over d tau is just gamma, and at earlier we used the speed of light in the gamma expression, and we know that the proper velocity xu over d tau, which is as dx over dt approaches to infinity. This term will actually approach as this term approaches the speed of light, this thing will approach infinity, because as an object goes faster, this value of proper time ticking more slowly, so this term will be smaller, and this term divided by this term will get to infinity, which is very different, and we have to be careful about the concept of proper velocity. But the chain rule might work here. So we know that dx, for example, dx over d tau may be equal to dx dt over d tau here times dx divided by dt. And yet that works, because this thing is gamma. We can say that gamma multiplied by dx over d tau, dx over dt. Okay, so dx over dt multiplied by gamma will equal to dx divided by d tau. So we can bring this to 2 here. So we have dx over dt. So let me just call dx over dt a velocity v normal. equal to V. So we would divide the dimension here. We will make this Vx, and we have the gamma with Vy, and we have the gamma factor with Vz as well. And this is our new adjustment. We can see that technically the force momentum vector multiplied by the velocity vector. The force momentum vector equal to mass times the force velocity vector. So we can distribute this. So we say that we must have this, where we have the gamma multiplied by mc and gamma multiplied by m Vx and gamma multiplied by m Vy and gamma multiplied by m Vz. And we can immediately realize that this is like the classical free momentum that we know. It's just mass times velocity. It's just mass times velocity, right? So this term is actually the normal classical free momentum, which just doesn't apply for relativistic speed, and we have to make a version of relativistic momentum, which is this term. So we can see here, this is actually the relativistic momentum here. So we can see that the dot product will give you this expression. So now we can finally move to the problem that we can have the momentum vector square, and it's equal to mass square times speed of light square. So we can move this, and we can write another vector. Sorry, just this norm. We can write this norm as mass square times speed of light square equal to the energy. Now for the energy part, we have to be careful because we have to look back at the force velocity vector. Okay, so I forget to show you that in this momentum vector, we can subtract the free spatial component to make a single component like this. So we reduce to 2 dimensions, so it's not looking too overwhelming. We immediately see that because we proved earlier that dt over d tau is speed of light, we can make this into the equation that we see is equal to gamma mc. And we remember that the classical low-range energy total energy equation is actually E equal gamma mc square. So this thing implies that's energy over speed of light, because gamma mc is gamma mc square over c. We see that energy here, so we have the component, the time component of the momentum is just energy, and we see the momentum for vector square is equal to energy square divided by speed of light square minus t's term. So we have here the problem of the photon. Now we can see that the problem with that we have, this is the classical for momentum, free momentum square. This is the classical free momentum square, which is equal to mass square times velocity square. This will be 0 for photon, and this term will be infinity. So infinity times 0 equal a constant. So we simply give up everything here, and we simply say that it had the relativistic free momentum, which is gamma mv. Let's just call this p equal to gamma m. The v I write as another color just still make sure that we keep in mind that it's the sum of free velocity. So we can write the momentum here square, and tada, we have the problem of we have completely derived the Einstein energy relation. So let me show you. So we can rewrite that this P here is actually m² c square equal to energy divided by speed of light square minus momentum square. Now I will write this blue thing as black too, because I think it's no longer necessary. So you keep in mind that it actually is the sum of three spatial dimensions. So this momentum actually is the total momentum in space direction. So it's no longer have the component x, y, and z. So just keep in mind that. So we have this term. And we can finally multiply by speed of light square. We have m² c to the power of 4 equal to e² minus p² c². And finally we have that famous energy relationship E² equal to m² c to the power of 4 plus b² c². And congratulations, for the mass of a particle is 0. We have this for momentum vector, which is a null vector now, is equal to 0. So this thing is 0. So we have 0 equal to E² divided by c² minus the free momentum, the free relativistic momentum p². And this means that E equal bc, which is consistent with this formula. Where if we set the mass particle to 0, this term will equal to 0. And we get that energy square equal to momentum square speed of light square, and we reduce to this equation as well. So this is the equation that applied to photon. So we completely have the energy momentum relationship right here. So it's pretty amazing. What it means that a person always had the component of momentum which is equal to the maximum object multiplied by speed of light, and the norm of momentum square is this term. It means that speed of light and mass is both constant, a kind of like, well, it's a conserved quantity though. It means that your form momentum is always conserved, but it means that the form momentum is actually equal to your mass, your rest mass, and which is 0 for photons. So the time component of the momentum of the photon is actually equal to its spatial component as well. So we have E equal Vc. So if you like the video, do not forget to leave a like and subscribe. Thank you.